Hello. In this video I'd like to talk about the acid-base properties of salts, and by salt we mean an ionic compound that consists of a cation and an anion. The skills we're going to acquire in this section include the following. Number one, given the formula of an ionic compound, determine whether it will form a solution that is acidic, basic, or neutral, and explain clearly why. And, under certain conditions, calculate the pH of a solution of an acidic or basic salt. So let's begin by considering acetic acid, a weak carboxylic acid. If I make a solution of acetic acid and test the pH, I find that the pH is less than 7. Why is that? Well, we know that's because acetic acid undergoes ionization in aqueous solution to produce the hydrogen ion and the acetate anion, the conjugate base, and the fact that the concentration of the hydrogen ion in the solution is greater than that of pure water means that it's an acidic solution with a pH of less than 7. But if I take a solution of sodium acetate, the sodium salt of the conjugate base of acetic acid, I find that the pH is greater than 7. That is, it forms a basic solution. Why would that be? Well, we can consider the following equilibrium. The acetate anion, being the conjugate base of a weak acid, is a stronger base than water. Therefore, it ionizes in aqueous solution to form acetic acid plus the hydroxide anion. And because it forms hydroxide anion at a concentration greater than that of neutral water, it forms a basic solution with a pH greater than 7. Let's consider ammonia. If I take a solution of ammonia, a weak amine base, and measure the pH, I see that the pH is greater than 7. Why? Well, because ammonia, as a weak base, ionizes in water to form the ammonium cation and the hydroxide anion. And because the hydroxide anion is produced in a concentration greater than that of neutral water, the pH is greater than 7. It's a basic solution. But if I take a solution of ammonium chloride, the chloride salt of the conjugate acid of the weak base ammonia, I find the pH is less than 7. Why is that? Well, that's because the conjugate acids of weak bases are stronger acids than water, and ammonia undergoes ionization to form ammonia plus the hydrogen ion, and since it forms the hydrogen ion in a concentration greater than that of neutral water, it forms an acidic solution with a pH less than 7. So, let's summarize. What kinds of salts produce basic solutions? Salts containing the conjugate base of a weak acid. So let's look at this. Here is a prototypical weak acid, HX, ionizing to form H plus an X minus. If I take a solution of the sodium salt of the conjugate base, NaX, because sodium salts are soluble, this will completely dissolve and dissociate to form sodium cations plus X minus, the conjugate base of HX. This second equation is not an equilibrium. I repeat, not an equilibrium. It is not governed by an equilibrium constant. It is only the source of X minus in solution. The equilibrium we want to consider is the weak base ionization of the conjugate base in water to form the acid plus hydroxide. This is the equilibrium, governed by an equilibrium constant that we'll deal with later, that forms a basic solution when you place the conjugate base of a weak acid in water. Likewise, we can ask the question, what kinds of salts produce acidic solutions? Well, as we saw, salts containing the conjugate acid of a weak base. Here's an equation representing the ionization of a weak base, which I'll show as B, forming BH plus OH minus. If I take a salt containing the conjugate acid of the weak base, BH plus, let's say, for example, the chloride salt, it will dissolve and completely dissociate, since chloride salts are soluble, to form a solution of BH plus Cl minus. This second equation, again, is not an equilibrium. I repeat, it is not an equilibrium. It is not governed by an equilibrium constant. It is simply the dissolution and dissociation of the salt of BH plus to form a solution of BH plus in water. The relevant ionization is BH plus ionizing to form BH plus H plus to form an acidic solution. This is the equilibrium that shows how BH plus forms an acidic solution. It is governed by an equilibrium constant we'll deal with later. Now, there's a second category of salts that produce acidic solutions, and those are salts that contain a cation with a high positive charge. What are some examples of these? Well, examples would include aluminum 3+, iron 3+, chromium 3+, etc. So how do these form acidic solutions? Well, the equation is as follows. I'm going to consider the hydrated metal cation MH2O6 3+. This indicates that there are 6 water molecules coordinated to the metal 3+ cation in solution. This undergoes ionization to form MH2O5OH with a 2+ charge plus H+. What happened here is one of these 6 water molecules coordinated to the metal cation lost a hydrogen ion in solution, forming the products that are shown. Why is this the case? Well, if I consider a water molecule coordinated by a lone pair to the metal cation, the high positive charge of the metal cation essentially behaves as a strongly electronegative element, pulling electron density away from the coordinated water molecule, weakening the OH bond, and making it easier for the hydrogen ion to come off as H+. And the product would be H2O5MOH, 2+ plus H+. Okay? So anytime you have a solution that contains a metal cation with a high positive charge, it will form an acidic solution. Now, what kind of salts produce neutral solutions? Well, salts in which the cation has a low positive charge. That would essentially include the alkali metal cations. So lithium plus, sodium plus, potassium plus, etc. These cations do not have sufficiently high positive charge to cause the polarization of the water molecule we saw in the previous slide. But also salts in which the anion is the conjugate base of a strong acid. Just as we saw earlier in the unit, the conjugate bases of weak acids are stronger bases than water, but the conjugate base of a strong acid has no tendency to attract a proton whatsoever. It is essentially neutral, therefore it will produce a neutral solution. So what are the conjugate bases of strong acids? Well, that would include the conjugate base of hydrochloric acid, hydrobromic acid, hydriodic acid, nitric acid, and perchloric acid. You'll recall sulfuric acid is also a strong acid. That's a separate case. I can explain that in class. So, how do we compare the relative basicities of the conjugate bases of weak acids? Well, the conjugate base of a weaker acid is a stronger base. So if I consider the basic ionization of X minus, the conjugate base of a weak acid, to form HX plus OH minus, the weaker the acid, the more the equilibrium will lie towards the products, because the greater the extent to which X minus wants to grab a proton and remain unionized, that will increase the concentration of hydroxide ion, making the solution more basic. How do we compare the relative acidities of the conjugate acids of weak bases? Again, the conjugate base of the weaker base will be, that should mean read the conjugate acid, of a weaker base is a stronger acid. So again, if I consider the weak acid ionization of BH+, the conjugate acid of a weak base B to form the base plus H+, okay? The weaker the base, the more the equilibrium will lie towards the products, since it really has no tendency to accept, or a weaker tendency to accept H+, that will increase the concentration of hydrogen ion, making it a stronger acid. So now comes the hard part. Let's go back one more. So let's use these principles to compare the basicities of two anions, each of which is the conjugate base of a weak acid. Which is more basic, cyanide or fluoride? Well, let's write out the equilibria for the ionizations. Cyanide with water to form hydrocyanic acid plus hydroxide. Fluoride plus water to form hydrofluoric acid plus hydroxide. Well, we said before that the stronger base will be the conjugate base of the weaker acid, so we have to go to our table of Ka values and look up the Kas. We see HCN has a Ka of 6.2 times 10 to the negative 10th. Hydrofluoric acid, on the other hand, has a Ka of 7.2 times 10 to the negative 4th. Hydrocyanic acid is clearly the weaker acid, therefore its conjugate base is going to be stronger, therefore cyanide is more basic. Which cation is more acidic, the pyridinium cation or the ammonium cation? Well, let's look at the equilibria for the ionizations. The pyridinium cation ionizes to form the conjugate base, pyridine, plus the hydrogen ion. Ammonium ionizes to form ammonia, the conjugate base, plus the hydrogen ion. Well, once again, we said that the stronger the base, the weaker the conjugate acid. Therefore, the weaker the base, the stronger the conjugate acid. So let's look up our Kb values. Pyridine has a Kb of 1.7 times 10 to the negative 9th. Ammonia, on the other hand, has a Kb of 1.8 times 10 to the negative 5th. Ammonia is the stronger base. It has a higher tendency to accept the proton. Therefore, pyridine, the weaker base, will form the stronger conjugate acid. Now we have to do some thinking. We have 5 solutions here, and we're going to arrange them in order from most acidic to most basic. The first thing you really want to do is to look at these formulas and analyze them to figure out what's the ion that we're most concerned about. Okay, so let's look at these sequentially. Potassium hydroxide, potassium salts are soluble. Potassium is a cation with a low positive charge. It's not going to have any acidic properties. Therefore, all we care about is hydroxide. Potassium chloride. Again, the potassium is irrelevant. We're only concerned about chloride. Potassium cyanide, we're concerned about cyanide. For ammonium chloride, chloride being the conjugate base of a strong acid is non-basic. Therefore, we're only concerned about ammonium. And finally, hydrochloric acid is a strong acid. It produces the hydrogen ion. So clearly, the most acidic of these is going to be hydrochloric acid. And the most basic will be potassium hydroxide. That's because hydrochloric acid is a strong acid, potassium hydroxide is a strong base. Can we judge what's going to go smack dab in the middle? Sure. We said before that salts in which the cation has a low positive charge are neutral, and salts in which the anion is the conjugate base of a strong acid are also neutral. That means potassium chloride is going to be neither acidic nor basic, so it's going to be in the middle. Let's see, we've taken care of this one, and this one. So that simply leaves ammonium and cyanide. Ammonium, the conjugate acid of a weak base, will be a stronger acid than water, but not as strong as hydrochloric acid. So ammonium comes next. And then finally, cyanide, the conjugate base of the weak acid hydrocyanic acid, is going to be basic, more basic than water, but not as basic as a strong base. So potassium cyanide comes next. So now let's get to some numbers. How do we calculate the pH of a solution of a basic anion? That is, if the anion is the conjugate base of a weak acid. Well, let's consider the weak base ionization of acetate, the conjugate base of acetic acid in water. Here's the equation. Kb is equal to the product of the concentration of acetic acid times hydroxide divided by the concentration of acetate anion. Again, we leave water out because it's the solvent. Its concentration is effectively constant. Well, if I look on my table of weak base ionization constants, I don't see acetate. But I do know that for acetic acid, I can write the Ka expression as the concentration of acetate times the concentration of the hydronium ion divided by the concentration of acetic acid, for which I have a number. So let's look at those two expressions and see how they're related to each other. What would happen if you multiplied those two equilibrium expressions together? Hey, let's try it and see. Ka expression is acetate times the hydronium ion concentration divided by the acetic acid concentration. My Kb expression is acetic acid times hydroxide over acetate. Hey, what happens here? Well, it looks like some concentrations cancel. Acetate cancels acetate, acetic acid cancels acetic acid, and what am I left with? What I have is simply that Ka for a weak acid times Kb for its conjugate base equals the product of the hydronium ion concentration times the hydroxide ion concentration, which is equal to Kw, which is equal to 1.0 times 10 to the negative 14th. This is hugely important. Okay? What this shows us then is that for any weak acid conjugate base pair or any weak base conjugate acid pair, or let's stop using those terms and just be much more general and call it an acid-base conjugate pair, because it doesn't matter which one we consider the acid and which one we consider the base, Ka times Kb equals Kw equals 1.0 times 10 to the negative 14th. So if you know Ka for a weak acid, you can use this to calculate Kb for its conjugate base. If you know Kb for a weak base, you can use this to calculate Ka for its conjugate acid. So let's summarize. If the cation has a low positive charge and the anion is the conjugate base of a strong acid, the pH is going to be neutral. Neither of those ions is acidic or basic. If the cation has a low positive charge, but the anion is the conjugate base of a weak acid, like cyanide, that will be acidic because because the anion is a stronger base than water. If the cation is the conjugate acid of a weak base, like ammonium, the anion is the conjugate base of a strong acid, that will be an acidic solution because the conjugate base of the strong acid is non-basic whatsoever, but the conjugate acid of a weak base is a stronger acid than water. The cation has a high positive charge and the anion is the conjugate base of a strong acid. The anion is not going to contribute to the acidity or basicity, but that will be an acidic solution because of the high positive charge, in this case, on the aluminum 3 plus cation. Finally, what if the cation is the conjugate acid of a weak base, like ammonium, and is therefore acidic, but the anion is the conjugate base of a weak acid and is therefore basic? Will the solution be acidic or basic? Well, it depends. Let's get rid of that. You have to calculate Ka for the acidic cation and Kb for the basic anion. If Ka is greater than Kb, the solution will be acidic because the cation will win out. But if Kb is greater than Ka, the solution will be basic because the anion will win out. If they happen to be equal to each other, which happens sometimes, then we would predict it would be a neutral solution. So here are some Ka, Kb values just for reference. Let's do some calculations. So I give you a solution of CH3NH3Cl with a concentration of 0.10 molar. We want to know what the pH is. Now, this is what I expect you to be able to do. You should look at that formula, CH3NH3Cl, and recognize, because it's got N some H's and Cl, that must be the chloride salt of an ammonium cation. And I expect you to be able to mentally dissociate this to form CH3NH3 plus Cl minus. Once again, this is not an equilibrium. It is not governed by an equilibrium constant. This is simply the dissolution and dissociation of this salt to form the methylammonium cation plus the chloride anion. Chloride is simply the spectator anion. It doesn't contribute to the acidity or basicity. The equilibrium we're concerned about will be the weak acid ionization of the methylammonium salt to form the conjugate base methylamine plus the hydrogen ion. Okay? So for this, we can write the Ka expression. So first of all, let's calculate Ka. So Ka for the methylammonium cation will be equal to Kw divided by Kb for methylamine, which is on our table of weak base ionization constants. So this is 1.0 times 10 to the negative 14th over 4.4 times 10 to the negative 4th. or 2.3 times 10 to the negative 11. Okay? Methylamine is fairly strong for a weak base, therefore its conjugate acid is going to be fairly weak, and that's what we see. So, to write out the Ka expression, Ka equals the concentration of methylamine, the conjugate base, times the concentration of the hydrogen ion, divided by the concentration of the methylammonium cation we were given to begin with. I'll skip the isotop table and go directly to this. With such a small Ka value, X is certainly going to be negligible. So I'll make a simplifying approximation. X equals the hydrogen ion concentration equals the square root of the initial concentration of the weak acid times its Ka value equals 1.5 times 10 to the negative 6 molar. By the way, folks, when you're doing these calculations to calculate equilibrium concentrations of hydrogen or hydroxide, please include the unit. That's what we do. So pH is the negative base 10 logarithm of, let's plug the value in, 1.5 times 10 to the negative 6, or 5.82. Again, also, please express pH and pOH values with 2 digits after the decimal points, and that is consistent with an acidic solution. In another example, calculate pH of a 0.050 molar solution of NaOBr, sodium hypobromite. Again, I expect you to look at the formula, analyze it, mentally dissect it into the ions that make it up, and recognize that this sodium salt, being completely soluble, will fully dissolve and dissociate to form sodium cations plus OBr minus hypobromite anions. Again, this is not an equilibrium. It is not governed by an equilibrium constant Ka or Kb. It simply shows the dissolution and dissociation of the salt to produce the hypobromite anion, which, being the conjugate base of the weak acid hypobromous acid, will undergo ionization in water to form hypobromous acid plus hydroxide. That's why it forms a basic solution. Now, we don't have Kb for hypobromite on our table, so we're going to have to use the fact that Ka times Kb equals Kw. So Kb of hypobromite equals Kw over Ka for hypobromous acid. I'll look that up on the table, and I see that that's equal to 2.0 times 10 to the negative 9th. So that gives me a value of 5.0 times 10 to the negative 6 for Ka. I'm sorry, Kb. I'll write out the Kb expression. Kb equals the concentration of hypobromous acid times the concentration of hydroxide divided by the concentration of hypobromite, or x squared over 0.050 minus x equals 5.0 times 10 to the negative 6th. Again, with a very small Kb, we'll make a simplifying approximation. And to solve, x is equal to the concentration of hydroxide equals the square root of the initial concentration of the weak base times Kb, or 5.0 times 10 to the negative 4th molar is my hydroxide ion concentration. So to finish the problem, pH equals 14.00 plus the base 10 logarithm of the hydroxide ion concentration, or 10.70, which is consistent with a basic solution. So let's finish up with one more problem that requires some thought. Are solutions of the following salts acidic, basic, or neutral? For those that are non-neutral, write balanced chemical equations for the reactions causing them to be acidic or basic. So again, the first thing you're going to do in each of these cases is to analyze the formula, split it up into its constituent cations and anions, and ask yourself, will this cation make the solution acidic? Will this anion make the solution basic? So NaNO3 consists of sodium cations and nitrate anions. Sodium has a low positive charge. Nitrate is the conjugate base of nitric acid, a strong acid, therefore it is non-basic. This, therefore, will be a neutral solution. Sodium nitrite consists of a sodium cation and the nitrite anion. Nitrite is the conjugate base of nitrous acid, a weak acid. Therefore, nitrite is a stronger base than water. Therefore, this will be a basic solution. And the equation will be NO2 minus plus water ionizing to form HNO2 plus hydroxide. C5H5NHClO4. What the hell is that? Well, I expect you to be able to look at this and see that C5H5NH will have a positive charge, which will be the conjugate acid of pyridine. ClO4 minus is the base, is the anion. Because perchlorate is the conjugate because perchlorate, ClO4 minus, is the conjugate base of perchloric acid, a strong acid, it's going to be neutral. But C5H5NH plus is the pyridinium ion. It is the conjugate acid of pyridine, a weak base. Therefore, it's going to be a stronger acid than water. So this will be an acidic solution, and the equation will be C5H5NH plus in equilibrium with C5H5N plus H plus. KOCl, you can look at that and recognize that it's made up of potassium cations, which having a low positive charge will be neutral, and OCl minus hypochlorite anions. Because hypochlorite is the conjugate base of the weak acid hypochlorous acid, it will be a stronger base than water. Therefore, this will be a basic solution. Hypochlorite will undergo basic ionization to form hypochlorous acid plus hydroxide. That's what makes it basic. Finally, ammonium nitrate consists of the ammonium cation and the nitrite anion. Ammonium is the conjugate acid of ammonia, a weak base, therefore it's going to be acidic. Nitrite is the conjugate base of nitrous acid, a weak acid, therefore it's going to be basic. Which will win out? Well, we have to look at the equilibrium constants. For ammonium, Ka equals Kw divided by Kb for ammonia, 1.8 times 10 to the negative fifth, which is 5.6 times 10 to the negative 10th. But Kb for the nitrite anion is equal to Kw divided by Ka for nitrous acid, which is 4.0 times 10 to the negative fourth, or 2.5 times 10 to the negative 11. Okay? We see here that the acidic component, ammonium, has a larger ionization constant than the basic component, NO2 minus. Because Ka is greater than Kb, we're going to say that this is an acidic solution, and we can write the equation that shows it behaving as an acid as NH4 plus, ionizing to form NH3 plus H plus. And that's all we have to say about the acid-base properties of salts. Thank you for your patience.